can hear you. This is very surreal.
Okay.
Thank you very much for the opportunity to speak. Is it time to speak now?
Yes, you can start, please.
Fantastic. Okay, so welcome to my talk, and thank you for giving me the opportunity. We're absolutely gutted that we can't be with you in Delft. Got a very high teaching load at the moment, and I've got a class just after this lecture. So just to introduce you to the team, myself, Nicholas Boydo. This is the work of our student Dan Rotherham, who's I think he might have one earphone listening at the moment, but he's also supposed to be in a class at the moment. My other authors are Ben Parks and Antonio Filipponi. Ben and Antonio and myself, we presented I think last year in the virtual or the hybrid event. So we're really happy to be back again. So this year we're talking about a piece of research that we've been working on for many years, actually, relating to dust ingestion into aircraft engines. And this is our first foray into using ADSB data to help us with this problem. And ultimately, we're aimed at predicting the dust mass ingested by aircraft engines in order to better predict maintenance scheduling and so on. So just to give you an overview of the contents of the presentation, I'll do a quick introduction, go into a bit more detail on the project background, and then we'll talk about the methodology. This is mostly of the work that Dan has been doing, so I'll try and do it justice, talk about the workflow, the filtering algorithms that we've used, and the coupling of the ADSB trajectories with ECMWF modelled weather data. And then we'll talk about the dose definition, which is the important indicator of dust mass ingestion severity that we've been using. And then we'll go into some results and talk about some initial findings that we've come across from this research. As I say, this is the beginning of the research, really. So I've seen some really nice talks already on some statistical analysis. We haven't done a huge amount of statistical analysis yet, but we do hope to in future, and we really will see, I think, the benefits of using ADSB for this problem. And then I'll talk about some conclusions and future work. So I'm not sure how well this is going to render on the presentation screen. You should hopefully be able to see a couple of pictures at the moment on the right hand side. The top right picture is actually the ECMWF CAMS reanalysis data being turned into an animation, a movie. And what you can see in the whiter areas are large swathes of dust moving around the Middle East. And you see actually it's Doha International Airport there in the green circle. So if we can get a pointer. Okay, so we see that there's lots of dust being brought into the region on a regular basis. The satellite data is shown in the bottom right, and it shows a fairly good overlap of the modelled dust concentration data and the satellite imagery. The way the satellite data retrieves or senses the dust is using an optical method. But you only get that on a daily basis and a once per day basis. So there's not quite enough fidelity there or temporal resolution to get us the data that we need to do our predictions. However, it does provide a useful verification source of information, and both these sources of data are publicly available. The NASA Worldview resource is really useful if anyone's not come across it before. So dust is a threat to aircraft engines. They're frequently occurring in the Middle East. The dust, when the dust concentration is particularly high, it can lead to visibility loss, and that's generally the reason why any airports are closed. They're not usually closed due to a threat of the dust to aircraft engines. It's not quite the same as the volcanic ash plume that emanated across from Iceland in 2010 and brought the airspace to a standstill for 6 days. Dust threat to engines is a bit more long term. There are many minerals within the dust that can chemically attack the metal components within engines, causing something called hot corrosion or sulfidation. You do get clogging up of cooling holes as well, so your loss of cooling effectiveness of the turbine blades, and you can the deposits can actually become molten and start to crack and spoil the thermal barrier coatings. So dust is a bit of a threat to aircraft engines, and they do curtail the lifetime of engines operating in these regions. And that's ultimately what the real motivation behind our work is to see if we can predict the peak ingestion periods and mitigate against further damage and effectively extend the lifetime of the engines. The burden is really twofold. For the operator, it's an increase in on-wing maintenance operations such as compressor washing, so that's increased downtime. For the engine provider, there are longer-term issues related to the reduction in the power provided by the engines. So it's usually on these total care or power by the hour sort of contracts these days. So it really affects how much power they're delivering, and ultimately they end up to swap engines in and out of the aircraft much more readily, much more often. So our research is really aimed at slowing that the degradation rate and mitigating against the damage. Our previous work on this subject, we've done some work very similar to this, but using a more of a great circle approach to the trajectories. We do have a standard climb out trajectory that we use, but we've done generally point-to-point great circle approximations of the flights, and we've flown those flights through the modelled dust concentration data, and those results did actually reveal some really interesting results, showing large peaks in the amount of dust ingested into the engines that correlated, of course, with dust storms in the region. As I said before, the airports aren't necessarily closed when there's a dust storm in the region, so aircraft are often taking off and landing in large concentrations of dust. But that great circle approach, which provided us some really interesting findings, it didn't quite capture certain nuances of operations in and around airports, especially busy airports in the Middle Eastern hubs like Dubai. So we didn't really manage to capture how often hold patterns were used. We didn't really get runway direction, and we weren't able to analyze the difference in ingestion levels between arrivals and the departures. So the Open Sky ADSB dataset we thought, well, we'll turn to this and see if we can find some really interesting things out about the differences between different route structures, different airlines, different aircraft. So that's the real basis for our use of ADSB. Switching to the methodology overview, and I'll have to just go to my notes here. So this is what Dan's been working on for the last couple of years, and it's building up this communication really with the ADSB network and the traffic API. So we have these inputs, which are our aircraft and fleet data. So we pick a particular airline in this case. So we have a whole fleet with several dozen aircraft in it, and we generate a flight list for a period of time. We selected March 2019 for this study. So what this flight list does is it pulls out all of the flights of that airline in that particular month of time, and produces us a list of hex codes, which allows us then to interrogate the ADSB database and pull out those trajectories. We then filter the flights for data quality and match the database with our own airport database to match the arrivals and departure airports to the target airport, which in this case was Dubai. There's some element of flight validation as well to ensure that flights are not throwing up spurious data, and to ensure that they did exist or they're not duplicated. And then once we're happy with all of the flights that we've produced, we then take the trajectories and we fly them through the modelled weather data, the modelled dust concentration data, to produce these plots of total dust ingested. Well, a metric known as dose, which I'll talk about in just a moment, which relates to the amount of dust ingested or exposed to by the engines. So we picked a particular low-cost carrier operating out of Dubai, and it was chosen really due to its range of flights operated, range of distances, and it had two aircraft that it operates. The 737 Next Gen, the Dash 800. It has 51 of those in its fleet, and it's got 10 MAX 8s as well in its fleet. So a couple of aircraft types, which made it a bit easier for the analysis, but also a range of destinations as well. We picked Dubai because the ADSB coverage is generally pretty good around that airport. We did lose quite a lot of destination airports, and we're not too worried about those because we're really interested in movements in and around the airport, so arrivals and departures into the airport from an altitude of about 10,000 feet. So we weren't too worried if we lost the destination airport, although we would ultimately like the full trajectories, and that's something we're working on. So here's a list of the flights. So we have arrivals and departure times, and as I said, we don't always manage to find the destination or origin airports, but what's most important is that we're capturing all of the flights into and out of Dubai, so OMDB there. So we generate this list of known flights for the aircraft. We store the basic metadata for identifying those flights. So that's the call sign, the hex code, the aircraft type, and then when it's first and last identified from its trajectory. There is an element of filtering, so we incorporate a fairly simple derivative-based filter here, looking at the changes in altitude over time to filter out those spurious jumps in altitude. So you can see here the blue line is our filtered data. The red line shows those filtered out data points, spurious data points. And we're using obviously the traffic software to pull the data in. We have a validation for our airports. So for the first and last points along the trajectory, we draw a circle around the airport of interest. In this case, Dubai International, 10 nautical mile radius, and a height envelope of 2,000 feet. And our airport is identified if the terminal trajectory points lie within that in that 3D envelope, 4D envelope actually, is a time-based envelope as well, of course, for the month of study. Segments with the data fraction greater than 90% are kept for further study. So we consider that to be a valid flight, and we take it on to the next step of the methodology. We did actually carry out a verification check of the ADSB data. There's a data set known as the In-Service Aircraft Global Observing System, or IARGOS for short, which is a fleet of about half a dozen aircraft that are flying around the globe. I think some Lufthansa aircraft, some China Airways aircraft, and they're fitted with atmospheric sensing probes that tell us pressures, temperatures. They don't tell us dust concentration yet, but that can be inferred from a probe called the backscatter cloud probe, which tells us levels of hydrous aerosol particles in the air. And if you combine that with relative humidity, you can kind of verify where there's dust present in the atmosphere. But you can see from the plot on the right, we also use this IARGOS data set to validate the flight trajectory itself. So it provides us with some flight data recorder data, which we can use to actually match the ADSB trajectory with. There is some deviation, and it does change over time as well, but we think that's due to some sensor miscalibration. It seems to reset itself every now and again. So you see the sort of zigzagging of the overlay of the altitude with the FDR data, the ADSB altitude with FDR data. So we assume that's maybe distance from the receiver, perhaps. We're not quite sure. Incidentally, this plot itself had I think it was Frankfurt into Kuwait International, and we actually lost the ADSB trajectory somewhere over Turkey there. But with the IARGOS data set, we are able to use that to complete certain trajectories, and We haven't mentioned much in the paper about this, but it'll come in a future work, our use of the Argus data set to validate ADSB and CAMS data sets. So in terms of the weather reanalysis, we use this atmosphere monitoring service, the EU provided data set. This is a reanalysis data set, and it contains aerosol mixing ratios, U and V components of wind, and of course temperature and pressure as well. We can get out of it predicted temperature and pressure. So you can see on the right hand side, this is a sample trajectory, just a dummy trajectory really. And what we do is we take that trajectory and we fly it through the CAMS grid cells. So there are 60, these grid cells are about 40 kilometers wide and tall, and they're spread across 60 pressure levels up to a maximum or minimum pressure level of 0.1 hectopascal. So they go really high up in the atmosphere, but they give us 60 discrete cells in the Z direction too. So what we do is we fly the trajectory through all of the cells, and we pull out the data from the specific cells that the aircraft has flown through. So you can see the cell interaction on the screen there. So as I said, it contains aerosol mixing ratios. So they're mixing ratios of kilograms per kilograms of dust per kilogram of air. And we take those kg per kg and we turn that into a kg of dust per unit volume of air. And that allows us to calculate something we call the dose. And the dose is becoming accepted as a way of expressing the dust exposure of an aircraft to a volcanic ash plume or a dust storm cloud. And it's a very simple calculation. It's simply the local concentration multiplied by the duration that the aircraft is passing through that concentration of dust. The reason why it's more useful than, say, the total mass ingested in a time period is because it allows us to normalize that mass and compare aircraft of different size and events of different dust type or aerosol type, so ash versus dust. And it allows us to then correlate the damage that results from the engine to a normalized parameter. So what we do is we fly that trajectory, as I said, through the cells. We pull out the local concentration of dust, we multiply it by the time period that the aircraft spent within that cell. And then along the trajectory, we just sum all of the different doses up and get a total dose for a particular trajectory. Just for context, this dose approach was used to produce kind of like a safe to fly limit for aircraft engines operating or flying through volcanic ash. And that safe to fly limit was expressed, I think, as about 14 grams seconds per cubic meter. So that gives you an element of context in terms of a dose level that's perhaps not threatening to engines, but if you go beyond that dose level, then rapid degradation effects start to take hold and it becomes a safety issue rather than a cost of ownership issue. The dose levels for ingestion of mineral dust in these environments is 1 or 2 orders of magnitude lower, so we're way away from the safety critical dose levels, but those dose levels that we do calculate do have that cost of ownership issue, which is why we're interested in them. So onto the study itself, we conducted this fleet level study. So we analysed in the month of March 2019 over 5,000 flights from this low cost carrier. Our filtering produced about less than 2,500 of those flights. About a third of those flights were usable, and that amounts to around 70 movements per day. And as you might expect, there's a 50-50 split on arrivals and departures. Each of those flights is flown through the CAMS data, and the dose is summed for each flight. We did pull out some erroneous dose levels that were getting towards those safety flying limits, and we looked at the data a bit further, and we found that our filtering algorithm hadn't quite pulled out all of the spurious flights. There were some flights that were kind of locked on a trajectory on an altitude of, say, 8,000 feet for several minutes, and that led to very large dose levels. So we introduced a criterion to pull out some of those dose levels, and if the dose was 1 standard deviation away from the mean for all aircraft, for all flights, we pulled it out and said, no, this is unrealistic. It's not likely to happen. Likely to be realistic here. So on to the results. So this is the dose levels throughout the month of March. We see the departures in blue and the arrivals in orange. And we can see fairly consistently the peaks and troughs occurring at around the same time, which is what we expect. The concentration levels, the CAMS cells are quite large, really. So the departures and arrivals are going to be flying through the same modeled data cells. However, the levels of dose are about 3 times higher with arrivals, which again one might expect because the arrival time is the aircraft is spending much longer in the air as it arrives into the airport. But to see the numbers is quite interesting to see. It's actually 3 times as high. We know Dubai frequently has holding patterns, so we think those holding patterns are leading to large amounts of dust being interacted with by the engines. We can see peaks around the 7th, 10th, the 18th, and 24th to 28th of March, and we think these are obviously representative of dust storms moving into the area, and that's the peaks kind of match with the peaks that we found in our earlier work as well. We know that March is quite a high dust storm activity month, so it's really interesting to see the orders of magnitude difference between sort of a normal ambient condition, let's say around the 5th of March, and then the dose levels when we do have dust storms moving into the area. So if you look at these dose levels, again, remember that 14 grams seconds per cubic meter being the limit for volcanic ash. So we're several orders of magnitude lower than that. But from 1 week to the next, we can see a huge increase in the dose levels. And those peaks, we think, as I said, are representative of dust storms in the area. We also looked at the influence of runway direction, and this provided, again, something that ADSB is giving us that we can't get elsewhere. We saw that with no Dubai International Airport has 2 directions, 120 and 300. Runway 300 is more commonly used outside of March, we understand, but here 68% were actually on runway 120. And we actually found that the dose was 2 times as high when the runway direction is 120, i.e. when the prevailing wind is a southeasterly. Southeasterly winds are common at this time of year. There's something called the Shamal winds. So we do see a bit of a wind switch direction between February and March of each year, and they tend to come across over from the Oman desert area rather than from the Persian or the Saudi Arabian desert. So that might tell us something about, I'll explain why the dose levels were higher. Is the dust composition or type from those particular regions of the Middle East, is it different in nature to the dust coming from the northwest? We also looked at the effect of altitude on dose. Dust concentration in general decreases with increasing altitude, but we can see from the departure plots, which are probably more representative of the concentration profile with altitude, that we do actually have a peak at around about 5,000 and 6,000 feet. And this peak we have seen this before in concentration plots during dust storms. And as I said, March is a very dust storm heavy month. And we think that this is showing us that when we have a lot of dust storms in the area, that peak concentration is not actually, although it's not exactly at ground level. And that's quite significant because the nature of the dust, generally, there's an assumption that what you find on the airport runway, if you take a sample and you do the chemical analysis, that's what the engines are seeing. But this plot is telling us that most of the dust is ingested at higher altitudes, i.e. dust that's brought into the area from somewhere else in the world. So it might be important when it comes to predicting how that dust damages the engines. The arrivals plot, we see a different pattern, and this is likely representative or reflecting the position of the hold patterns on arrival into the airport. So we see peaks at 6,000, 7,000 feet, even as high as 9,000 feet, large doses that the aircraft is interacting with. So there was just a snapshot of some of the results we've done so far. As I said, we haven't done a lot of analysis yet. This is quite a new area for us, and Dan is going to be working on this in future, and and hopefully making more contributions to this seminar. About 43% of the flights that we, just to conclude, 43% of the flights were considered usable and we've flown through. We found a mean dose to be about 0.0386, which is approximately 50 times less than that safe to fly dose threshold for ash. But when we have those dust storm activities, that mean dose jumps by a factor of 10. The runway direction was found to greatly influence dose. Movements to and from runway 120 were found to experience a dose over 2 times that of runway 300. Altitudinal variation does depend on departure and arrival, but the departures tend to reflect the dust concentration over the month, the average dust concentration over the month. But arrival has no real clear pattern and probably is skewed by the holding pattern, contamination, let's call it. So we do need to do further work to better understand the nature of the dust storms and extend the time range of the flights. A few areas of interest for future work, that's statistical inference. Can we apply some regression analysis to better identify these variables that are introduced by realistic flight trajectories and allow us to predict, for example, the probability of dust storms? We want to perform a full year study, apply it to a long haul carrier and look at other airports such as Doha International. And of course, then, as I mentioned, validating the dust mass ingestion with the ARGOS dataset. Okay, so I think that concludes all of my work and I am happy to take any questions. Just to acknowledge not only my other authors, but the verification dataset was obtained through an impact acceleration account award. And I want to acknowledge as well Professor Martin Gallagher and Gary Lloyd of the University of Manchester for their contribution of the ARGOS dataset. So thank you for your time and I'll happily take any questions.